Okay, this is a pretty intense example. This is finding all the zeros of a polynomial and then getting it into a linear factorization. So I'm going to tell you have one zero at 1 minus 2i, which automatically that should tell you that your other zero is at 1 plus 2i. Now there are two very different ways to handle this problem. One is messy and very calculator active, and the other is not so messy and not calculator active. I'm actually going to start with the not so messy part. These are two zeros. So I have one zero at x equals 1 minus 2i, and I have another one at x equals 1 plus 2i. Now the idea is I want to factor these out eventually from that fourth degree polynomial, that x to the fourth business. Before I decide that I'm going to factor them out, when we talk about factoring things out, we can also kind of talk about, well, factoring out is the same as kind of dividing them out. So I can divide this guy out and I can divide that guy out. You can do synthetic division. You can also do long division, and I really do think that this is the easier version. If these are both factors of this, what I can do is I can create the two linear factors. So all I did was kick one over and that imaginary part over. When I multiply these through, I'm going to get a second degree, but that second degree is not going to have any i's because of the fact that I'm using conjugates. So x squared minus x minus 2xi, negative x plus 1 plus 2i, 2xi minus 2i minus 4i squared. Those guys cancel. These guys cancel. This is minus 4 minus 1, so plus 4. So the resulting quadratic I have is x squared minus 2x plus 5. This is the product of these two, which means it needs to be a factor of this. So what I like to do is I just multiply those two kind of ugly imaginary parts, and then I use long division to divide it out. So I had x to the fourth, 4x to the fourth, need a placeholder. So the first one I have is 4x squared hanging out up there. Subtract everything through. 8x cubed is going to lead the way, so your next one is going to be plus 8x. Once I multiply that 8x through and subtract, I'm left with 13x squared minus 26x plus 65. So my next one is going to be plus 13. And when I multiply all of that through and subtract, my remainder is 0. So this tells me that this is a factor, and the way that we got there was through multiplying our two known complex zeros. So I took that out, and my quotient is basically what I have left over. Now remember, if I multiplied these two things, it would take me back to that fourth degree polynomial we started with. Your end goal is to find all of the zeros. You want to get it in some form of a quadratic. This is a quadratic that you can use the quadratic formula on. So we have negative 8 plus or minus 64 minus the quantity 4 times 13, all over 2 times 4, which is 8. Negative 8 plus or minus radical, negative 144, all over 8. Negative 8 plus or minus 12i over 8, which is going to simplify down into negative 1 plus or minus 4/3 I. So those are our other, zero, so x equals negative 1 minus 4/3 I, and x equals, what was our very one at the beginning? 1 minus 2i. So you just want to get these in linear factor form, so I'm going to multiply everything by 3, so 3x equals negative 3 plus 4i, so 3x plus 3 minus 4i. Everything by 3 again, 3x equals negative 3 minus 4i, so that's going to be 3x plus 3 plus 4i. These are fine, so x minus 1 plus 2i, x minus 1 minus 2i. Ugly, but this is exactly the linear factorization. So this guy is never going to touch the x-axis. If I was trying to do a sketch of this, it's going to be some fourth degree, but he's never going to come down and actually touch that x-axis. He has 4 zeros, he has 4 roots, and we kind of have listed them. Here's your zeros, your roots. This is the linear factors, no x-intercepts though. That's kind of bringing together all those ideas with the fundamental theorem of algebra. This is the basic non-calculator way. It's very limited calculator usage. The next method that I'm going to show you is very calculator dependent. It can be really confusing. So I would really maybe try both methods and see what you're comfortable with. But just going to kind of rework and go through this again. This is your first known zero, which gave me my second known zero. I converted those known zeros into their linear factor form. I multiplied them to get a nice, beautiful quadratic. I factored out that quadratic, the known factors of that fourth degree polynomial, and my result was this nice quotient, 4x squared plus 8x plus 13. Once I had a nice second degree quotient, I used the quadratic formula to find my other 2 zeros, which happen to also be complex. Here are all 4 of my complex zeros, and I converted them into linear factor form.